I'll use this. Hello. Yeah. Welcome to the keynote talk of the day. The speaker today is Tim Roughgarden. Tim is one of the leaders of the field. He's written several books on algorithmic game theory that have been very influential. He's a professor at Stanford, and he's won many awards. I think I'm going to embarrass him by actually trying to list all the awards he's won. It's going to take some time. It's a long list. So he's won the ACM Grace Murray Hopper Award, the Presidential Early Career Award for Scientists and Engineers, the Kalai Prize in Computer Science and Game Theory, the Shapley Lectureship of the Game Theory Society, the Social Choice and Welfare Prize, Inform's Optimization Prize for Young Researchers, the Mathematical Programming Society's Tucker Prize, the Gödel Prize, and the Guggenheim Fellowship. So it's my great pleasure to welcome Tim. And Tim has started many lines of research that have been really fruitful. And one of my favorite lines of research that he has started is this sample complexity of auctions. And I think he's going to talk about that. So I'm very excited to hear him speak. Over to Tim.
Is this working? Check 1, 2. All right. Thanks very much, Nikhil, and thanks also to the Wine Organizing Committee. It's definitely a privilege to be able to be here and give this talk. Also my first trip to India, so very exciting. So as Nikhil mentioned, what I want to talk about today is a topic in algorithmic game theory which has really just totally exploded over the past couple of years. Lots of people are doing great to be the winner of the auction. Meyerson proved, doesn't matter what the Fs are, what the distributions are, this is the optimal auction. Okay? So that's very satisfying mathematically. Moreover, if you actually restrict attention to the important symmetric case, meaning bidders who have IID valuations all drawn from some common distribution, F, then actually this description simplifies tremendously, and we get as the optimal auction a very familiar auction format, just the Vickery auction with a suitably chosen reserve price. In other words, eBay is actually optimal for the symmetric problem. And this is kind of incredible, right? This is like a huge win for theory, because there's lots of weird auctions in the world. And so what you do here is you optimize over all of them, and over all of the sort of exotic creatures that you could have done, it turns out the theoretically best one is this eminently practical and widely used auction format. So it's a great confluence of theory and practice. Now in the asymmetric case where the FIs can be different, it's not so simple. Okay, really you can't simplify the description of the optimal auction beyond what I've put here. So you really do have a detailed dependence on exactly what distributions you assume. So that's sort of classical optimal auction theory. Now suppose you wanted to kind of take an engineering view of things. Suppose you wanted to make this theory operational and really apply it in a real setting, in real auctions. What would be the impediments? Well, there's a few, but the one I want to focus on today is the informational assumption made here that the auction designer is fully aware of what these distributions are, F1 up to Fn. Okay, I want to relax that informational assumption. Right? Where do these distributions come from? All right, so if you wanted to apply this in practice, how might you proceed? Well, you might try to estimate what the distributions are. Estimate from what? Well, the people in this room, I think the answer is sort of obvious, estimate from data, okay? So to apply this optimal auction theory, you need to somehow formulate a prior. Where does it come from? Presumably from data in the form of bids in previous auctions, hopefully by sort of similar bidders, hopefully for similar items, okay? And this is not just, it's a natural idea, but it's really used. And the most well-documented application is a very nice field study by Ostrowski and Schwartz. So they're contracted by Yahoo to help them think about their reserve prices in their sponsored search auctions. And Ostrowski and Schwartz did just what we said. They said, well, what would Meyerson tell us to do? Or wait a minute, I guess we need to sort of figure out our priors. Well, Yahoo was very happy to give them tons of previous bidding data, so they fitted valuation distributions using that bidding data, then they just applied optimal auction theory to see what it said. And what it recommended was to raise the reserve prices actually a fair bit on certain types of keywords. And Ostrowski and Schwartz actually convinced Yahoo to do that. Okay, they convinced them to raise reserves on sort of high-value keywords, and as a result, Yahoo actually made significantly more money, to the point that in one of their quarterly earnings reports, reserve price optimization was actually singled out as the major reason why their search engine revenue increased. It was a big deal. Unfortunately, I don't think Ostrowski and Schwartz were paid by commission. They would be doing really well if that were the case. So. All right, so suppose you wanted to do theory around these kinds of ideas. What questions could you ask? Well, one of the simplest questions would just be a purely statistical question, right? So presumably, the more data you have, the better your data sets, the better job you're going to be able to do of maximizing revenue. So exactly what does that trade-off look like? As a function of how much data do you have, what kind of revenue approximation can you enjoy? For example, you might say, I want a 1 minus epsilon approximation of the theoretically optimal auction, assuming I knew the distributions, so Meyerson's auction. And you could ask, as a function of epsilon and the other parameters of the setting, how many samples are necessary and sufficient in order to achieve that? And what does the learning algorithm look like? Okay, so just to be clear, when we say data, so now mathematically what we mean is we're assuming that these FIs really exist. So we're continuing to assume that valuations are drawn from some distributions. We're just not assuming we don't know what they are, except in as much as we have data, meaning IID samples from these unknown distributions. Okay? All right, so that's kind of the preamble. What I want to do next is drill down into exactly these kinds of statistical questions. How much data is necessary and sufficient for good revenue approximation? So any questions before I drill down into the statistical part? Okay. Yeah.
Are these FIs independent?
They're independent, yeah. Yeah, optimal auction theory kind of goes a little haywire if you don't assume that they're independent. So somehow, even if you know in reality things aren't independent, you still somehow often get better advice from auction theory if you assume independence, turns out. Yeah. Other questions? Yep.
Is there a minimum value of n you need for optimality?
No, even for n equals 1, this is quite an interesting problem. Yeah. I mean, there's a sense that, it sort of depends if the bidders are similar or dissimilar. If the bidders are similar, then you're only doing better as n grows large, because then you can use everybody's past bids to reason about everybody else. But in general, these have nothing to do with each other. In general, they're idiosyncratic. Yeah.
Are they restricting this FI using some parameter, or it is just?
That's a good question. So you do need to make some kind of assumption. For today, just think of them as having bounded support, and otherwise being arbitrary. There's other assumptions you can make, but that's a simple one to keep in mind. Yeah. Yeah. Yeah, that'll be the very last part. That'll be the strategic aspects. Yeah. Okay. Good. So Nikhil's point, just to foreshadow sort of what's coming later, is I've been talking about bidding data, and actually in the theory I'm about to do, I'm actually going to be assuming you get valuation data. Okay, that is, I'm going to be assuming truthful bids in your data set. Or really, all you need is that you can reverse engineer the values from the bids that you see, which is a weaker assumption. But we'll come back and address that assumption at the end of the talk. All right, so let me talk a little bit about sample complexity. And the work of mine in this part will be joint with Jamie Morgenstern of Georgia Tech. So, again, the question we're trying to understand is how much data, how many samples are necessary and sufficient to get close to the maximum possible revenue, the benchmark of what Meyerson's auction would achieve if you knew the distributions and could run it. So asymptotic versions of this question were studied a fair amount last decade. So these are results which say, well, okay, well, at least let's have the sanity check that let's look for an auction where as the number of samples goes to infinity, the revenue converges to 100%, converges to the optimal solution. Okay, so fix a distribution, let the number of samples go to infinity, and then prove an approximation guarantee. What I'm interested in here, which is much more in the spirit of sort of machine learning theory, is quantitative and uniform bounds. So I don't want to fix a distribution first and then start analyzing how many samples I need. Right? The whole point of this is that I don't know the distribution. So I want to have a single, finite sample complexity bound that no matter what the distribution is, maybe under mild technical assumptions, but essentially no matter what the distribution is, I have a guarantee that I'm going to be learning nearly the best auction. Okay, so that's sort of a different quantitative approach, uniform bounds for finite samples. A couple precursors to when people started really studying this in earnest. Edith Elkin had a very prescient paper in SOTA 2007. She was thinking about kind of a local search algorithm for finding the optimal auction if I give you an oracle which allows you to compare the revenue between two different auctions. But still it anticipated the sample complexity results I'm going to be talking about. Also, I did some work with two former PhD students, Pierpong Dangwanatai and Zhiyi Huang. The point of that paper was to develop what we called the theory of prior independent auctions, auctions that are approximately optimal simultaneously for a wide range of distributions. But it turns out some of the lemmas that we proved to derive those results really foreshadowed what was going to happen in the sample complexity results that I'm going to tell you about. 2014 is when sort of a bunch of people just independently started working on kind of exactly this problem, sample complexity of revenue maximization, including a wine paper actually from a couple years ago. And now, I don't know how many of you know this, because strangely this topic is actually not well represented at this year's wine, but this has really kind of totally exploded. Okay, there's really been, this is not a complete list, but there's literally been at least, say, a dozen papers in 2017 on exactly these kinds of issues. All right? So what I'm going to tell you about in this part of the talk is I'm going to tell you a little bit about my work with Jamie Morgenstern. There's a paper from NIPS 2 years ago and Colt last year. What we do, we give what's in some sense the most systematic approach known for deriving reasonable sample complexity bounds. But I should say for a number of different specific settings, these subsequent works, including some by people in the room, do improve over our sample complexity bounds in specific cases using kind of customized arguments. Okay? All right, so I should also say that auction theory isn't the first part of algorithmic game theory to make use of statistical learning theory. In particular, Ariel actually has a couple of very nice papers about learning voting rules from samples. So I give you a bunch of examples of maps from preferences to outcomes, and you have to figure out what voting rule is being used to make those decisions. But even though some of these are quite a bit older than all this work in auctions, it seems empirically that auction theory has emerged as the killer app in algorithmic game theory for using machine learning theory to learn from unknown distributions. Okay. So let me tell you what the actual model is, okay? And this is inspired by standard statistical or packed learning theory, a la Vapnik or Valiant. So we assume they're a distribution. So again, there's n bidders, let's say one item to keep it concrete. They have distributions f1 through fn. They exist, but you do not know what they are. At the time that you have to decide on what auction you want to run, you know about these unknown distributions only in as much as you know S samples from the distribution, okay? And so to be clear, a sample here is actually an n vector. It's a valuation profile with one draw for each of the n bidders. So you're actually getting n times S different real numbers, okay, in this input. All right, so you get S samples, again, which we interpret as sort of bidding data from past auctions with comparable bidders for a comparable item. On a basis of these alone, the seller or the auction designer picks an auction, truthful auction, say, and then we're going to assess the quality of this auction that was chosen according to its expected revenue on a new sample from the same distribution. Okay? So when we choose A, we know these, but this we don't know. Okay? And this is our sort of test set, if you like, for understanding how good an auction did we pick. So here's the schematic. So what do we want? Well, we want to be close to opt. What is opt? Opt is just, it says, suppose you actually knew those distributions and suppose you actually implemented Meyerson's optimal auction. You would make some amount of money, $10,000, whatever. So that's opt, and we would like our revenue to be almost as good. Okay, our revenue is going to be, there's two sources of randomness. First, there's in the samples. So you can look at the expected value over the samples and then also over the fresh sample of what our revenue is. Okay? You can also ask for a stronger version, which would be with high probability over the samples. That's also interesting. But let me just put this on the slide. Okay? So I hope it's clear. Right? So samples come in, you choose an auction, and then you're going to have some expected revenue on future valuation profiles drawn from the same distribution. You'd like to compete with the best auction with full distributional knowledge.
Okay, so when you say choose an auction, you mean just choose the reserve price or is it something else?
Good question, yeah. So everything's going to be parameterized by a class of auctions that you care about. And it's going to be interesting to vary the class. So for concreteness, I think for now it's totally fine to just think that you're picking a reserve price. Yeah. But I'll be more explicit about the auction class shortly. Okay, good. So that's kind of the picture you should have in mind. Everyone okay with that? Any questions? Yeah.
You have same number of samples for each figure, or you have missing the item?
Yeah, I mean, if you want, you can sort of have some probability that you have a zero value to stand in for some bidder or type of bidder didn't show up. Yeah, so there's various sort of extensions that can be sort of shoehorned into this model. But for simplicity, just think you get n-numbers every time, and the ith number is always drawn from this distribution F5. That's the simplest thing to think of.
So we're discussing only single item.
Yeah, so I encourage you to think in your mind about single item auctions, just because why not? It sort of illustrates all of the key issues. A lot of the results that I'll talk about today go beyond single item auctions. Some of them are sort of stuck with single parameter type problems. Some of them have multi-parameter analogs. At times I'll talk about that. But in general, just to get the sort of main narrative of the talk, you'll get the whole thing if you just think about single item auctions. So kind of a pro tip. Okay. All right, so what did we want to show? So when Jamie and I started working on this problem, we really wanted to stand on the shoulders of learning theory. Right? We knew there were all these great tools in learning theory for understanding prediction problems, and you also get some very crisp sort of lessons and guidance out of it. Like one thing you learn just in the first few lectures of an intro learning theory class is you learn about notions of complexity of different hypotheses, of different functions. And there are these really cool results which basically say if you have a priori knowledge that what you're trying to learn is pretty simple, then actually you don't need much data to do it. Whereas if you don't know that, if what you're trying to learn might be very complicated, then you might need a lot of data. So like linear functions are easy to learn from a few samples, but high degree polynomials are much, you need many more samples to accurately learn them. So that's all kind of stuff, 20th century stuff that's been known for a long time. So Jamie and I were wondering what would be the analog in the context of learning good auctions. Could there be some sense in which simple auctions are easy to learn and complex auctions are hard to learn? Okay. So to implement that agenda, we obviously need to commit to some definition, mathematical definition, of what it means for a mechanism or class of mechanisms to be simple or complex. So that's what I want to tell you about next, the complexity measure that we wind up using for these problems. But first, actually, let me say that this question of formally defining notions of mechanism complexity, it actually dovetails nicely with a different kind of very active area of research in algorithmic game theory, which is proving approximation guarantees for relatively simple mechanisms compared to complicated optimal mechanisms. So for example, one relatively old result of this form, so Jason Hartline and I wrote a paper, which we called Simple versus Optimal Mechanisms. And our results had the form of like looking at single parameter problems, taking just reserve price-based auctions, so just the VCG mechanism on top of reserve prices, which is not in general optimal, is not Meyerson's mechanism, and trying to identify conditions under which it's close to the revenue of Meyerson's mechanism. Okay, and you can prove results of that form. So we called the paper Simple versus Optimal. That was actually the title. But it's not like we ever defined what was simple. It was subjective. We kind of left it as self-evident that, these reserve price-based mechanisms are, simpler in some sense than those crazy virtual welfare maximizers that Meyerson needed. But we didn't define it. If you'd sort of backed me into a corner and said, Tim, no, really, what do you mean? Why do you say that? I probably would have mumbled something about degrees of freedom, right? So the option on the left, the only options you have available to you is to set personalized reserve prices, so one per bid. So that's like n degrees of freedom. The right-hand side, remember we had that virtual bidding function phi, which can be chosen however we want. So you can choose total, you can choose entire functions. So that kind of felt like an infinite number of degrees of freedom. Okay, so that was sort of the vague intuition we had at the time. Since this paper, there's been lots of great, more difficult, more general results along these lines. So like one famous one is a Fox 14 paper by Bob Bailoff and Malika Lucier Weinberg, who look at a multi-parameter problem. Okay, it's one of the most basic multi-parameter problems, single buyer, multiple items, additive valuations. In general, the optimal mechanism can be super complex, kind of unknowable almost. And yet, there's a simple mechanism, namely either you bundle all the items together and sell it for a take it or leave it offer, or you just put a posted price on each item and let the bidder take whichever subset they want, okay? They prove that one of the two of those is always within a constant factor of the optimal mechanism. And here again, intuitively, the number of parameters feels like it's limited. Okay, so what do you have to choose? Basically, the price for the grand bundle, a price for each item, and maybe like you also choose which of the two you're going to do. So let's call it k plus 2 parameters, okay? And there's been many generalizations of this since. All right, so let me now actually get to the proposed complexity measure. And it's not, so the good news is we don't need to invent a new one. Okay, we can really just make use of a standard one in statistical learning theory. And so the notion is something called pseudodimension. And please accept my apologies. Actually, in the interest of time, I'm not going to formally define pseudodimension for you. I will say that if you've ever seen the definition of VC dimension, this is basically exactly the same, just for real valued functions rather than for 0-1 valued functions. If you've never seen VC dimension before, just it's some measure of complexity for how many diverse behaviors a given class of functions can exhibit, okay? So I will tell you about why you should care about the definition, right? And again, to care about any definition, I really need to tell you two things: compelling examples and interesting implications of meeting the definition. So those two things I will tell you, okay? The one thing I want to be clear on is, so pseudodimension, it's a complexity measure for collections of functions. And we're thinking about collections of auctions, okay, like a single item auction with all possible reserves. That's what we want to think about. So we need to think about auctions as real valued functions. But that's actually easy enough, right? So for any fixed auction, if you feed in a bid profile, you get out some revenue. Okay, so the domain of our function is going to be all possible valuation profiles, and then the output is the revenue of that auction on each valuation profile. So you can think of a one-to-one correspondence between the auctions in your class and the corresponding revenue function. Okay? All right, so that's the pseudodimension. So examples. Well, so the first thing I want to just point out, so this is a well-defined number, no matter what family of auctions you're thinking about, no matter how weird they are. If you instantiate it in specific cases where we have strong intuition about how complex we think the class is, you get back very sensible results, okay? So like if you're just trying to pick a reserve price in a single item auction, like on eBay, then, which feels like 1 degree of freedom, the pseudodimension is indeed constant. I believe it's 2, I think. If instead you're allowed to use personalized reserve prices, 1 per bidder, so this was like a couple slides ago, that felt like n degrees of freedom. In fact, the pseudodimension's O of n log n at most. My guess is there's some sloppiness in our proof and we could probably get n, but certainly it's no higher than n log n. Similarly, with the single item, single buyer k item case, again, the pseudodimension is scaling basically linear in the number of items, conforming to our intuition, okay? So this is good. This is a sanity check. The pseudodimension seems to be doing the right thing for classes of auctions that we know and love. All right, so those are examples. What about implications? Like, why should you care if a class of mechanisms has small pseudodimension? Well, the reason you should care is because if you have small pseudodimension, then you have small sample complexity. So if you are simple in the sense of having a small pseudodimension, then it's easy to learn what to do, okay? In the sense that you do not need many samples to be able to get a 1 minus epsilon approximation. Okay, so a little more detail. Here is the sample complexity required. Epsilon and h, these are just kind of scale parameters, so I would encourage you to ignore these. And the key thing to notice is that the sample complexity is scaling linearly in the pseudodimension d, okay? This is the number of samples necessary that are sufficient in order to get a 1 minus epsilon approximation, to pick an auction which is almost as good as the best one. So, for example, if you just need to learn 1 reserve price, an anonymous reserve price, this is going to be constant sample complexity, okay, for constant h and epsilon. If you're learning personalized reserves, the sample complexity will be scaling with a number of bidders n. If you're learning sort of the best way to price items or price the grand bundle, the sample complexity will be scaling with k, and so on. Okay? So that's why you should care. It's a sufficient condition for low sample complexity. You might wonder about, what actually is the learning algorithm, right? So given a bunch of samples, how do you actually, what is the auction from the class that meets this 1 minus epsilon guarantee? And it's actually probably the first thing most of you would think of. It's something known as the ERM learning algorithm. Okay, in machine learning, that usually means empirical risk minimization. But here, we can think of it as empirical revenue maximization. And we can keep the same acronym. So what does that mean? That literally just means get all your samples, get your valuation profiles, look at the classes of auctions, the auctions you're willing to implement, and among everything you're willing to implement, figure out which one does the best on the samples, has the highest average revenue on the samples that you've seen. And just hope that the samples that you've seen are representative of the samples you're going to see in the future, and just use the mechanism which is best on what you've seen in the past. Okay? And that sort of conceptually very simple algorithm is exactly the one for which this guarantee holds. Okay? So with high probability, if you have this many samples, the output of the ERM learning algorithm will in fact be with an epsilon of the expected revenue of the Meyerson optimal mechanism. Okay? So any questions about that? This is most of what I wanted to say about the statistical aspects before I get into algorithms. Okay, yeah.
Basically, the computing will enable for all functions which are in the class.
Good, yes, conceptually, yes. So conceptually, you sort of enumerate every option you're willing to implement one by one. You compute each of them, you compute the revenue of each, and whichever had the highest revenue on the samples you've seen, that's the one you'd like to use in the
But if
future.
your class is very large.
Right, so that's exactly why we were segueing into sort of algorithmic issues. Okay, so far I've said nothing about efficient learning. I've just said in principle what we can do. Yeah.
So for example, if you are, single item reserve, single reserve price is your class and your data is V1 to Vs, where V1 is the highest, you would pick a reserve of V1. Is that what the empirical risk, what the M star mechanism would be?
I don't think so. So I think this will probably be, actually I have a detailed example in a few slides that I think will make this clear. Yeah. So I mean, the question is basically what does the relevant computational problem here look like? And that's exactly what I'm going to talk about next. So, yeah.
You're looking at the product distribution or?
Yes. Although, in fact, that's not important. So the statistical learning theory stuff makes sense even on spaces that don't have a product structure. So they would actually hold even for correlated. So the sample complexity bounds would hold even for correlated distributions. It's just that the classes of options that we think about, usually we're thinking about options that are optimal or near optimal under some assumptions. And so the options we look at are sort of justified under independence assumptions. But the learning results actually hold anyways. So you'll still learn the best option in your class. It might just be that all options in your class are pretty bad.
So the VI is a vector, right?
Yes.
So you're looking at product, you're not constructing FIs per se, you're just looking at.
Oh, good point. Yeah, you're not constructing FIs per se. Yeah. One work by Nikhil and Zhiyi Huang and Aksomas, they do actually, for reasons of efficiency, they do actually marginalize each bidder, and then they actually compute an F hat I for each bidder, and then you actually just use Meyerson for those F hats. So you need to do some work to kind of show that you can get away with that marginalization doesn't hurt you, given that the original distribution is a product. But that's not what we're doing here. So you're absolutely right. We're not actually literally forming estimates of the Fs. We're just, if you like, the sort of uniform distribution over the samples is kind of our estimate of F, which is a correlated distribution. But it's okay. Yeah. Yeah.
Is there the role of revenue equals thing here in reducing the complexity?
Yeah, so the question was about the revenue equivalence theorem. I mean, the pseudo dimension only depends on this induced function, right? So in some sense, two things that are revenue equivalent are going to be treated as if they're literally exactly the same function by this theory. So, I mean, yeah, so that's the thing to remember. So this complexity measures depends only on the input-output functional behavior, not on how it's implemented. So any given implementations that have the same revenue properties will have exactly the same properties for this type of definitions. Yeah.
Using some idea of cost validation, how people use data.
Right, so that's a good question. I mean, I think this is something people are probably starting to look at, and I really think should be explored in more detail, right? So, but I have to say, I mean, these are issues we sort of don't understand super well, even in just straight up binary classification. So the question is sort of, what do you do if you don't have this much data, right? So maybe you want to actually optimize over a complex family of auctions, and actually the amount of data you have is scarce enough that you don't get any good guarantees. What can you do? And so there's this whole machine learning toolbox, like regularization, et cetera, that you can use to try to combat overfitting. And I think it would be very interesting to have, analogs of this theory in sort of the undersampled case, But again, like my understanding is that the state is fairly primitive, understanding those kinds of questions, even for the most basic classification problems. But I love the direction in general. Okay, so let me talk about algorithms. And so what I'll talk about here is based on work with Josh Wang, who's a brilliant PhD student of mine, graduating this year and looking for postdocs. So be on the lookout for Josh. Mostly from an EC paper from last year, but also some under submission results. So this came up in one of the questions, right? It's fine to say, okay, the algorithm is pick the auction from your class, which is best on the samples, but like, how do you actually do that, okay, efficiently? Especially, I mean, the auction class might even be infinite. So how do you actually do this? How do you implement it? So now getting back to Nicole's question, let's actually think carefully about what this problem actually is, what an algorithm might look like. So the problem you need to solve to implement the ERM algorithm is I give you a bunch of valuation profiles. It used to be S, now it's T, for reasons that will become clear. I give you a bunch of valuation profiles. I give you some class of auctions, like single item auction, maybe with an anonymous reserve, or single item auction with bidder-specific reserves. And among all auctions in C, or all choices of reserves, make this as big as possible. Okay? The total revenue you would get summed over all of the valuation profiles that you have. Okay? This is exactly the computational problem that you need to solve to implement the ERM algorithm. Okay? So I'm going to call this the offline problem, because you're given all of these up front in a batch. Okay? I give you a bunch of valuation profiles. What would have been the best in hindsight had you known those would have been the valuation profiles? Okay? All right, so now I want to actually think about this problem a little bit from a computational complexity perspective. Right? So is it NP, is it NP hard, et cetera, et cetera, et cetera. Okay, so I think it's a very natural problem. All right, so, and let's, I mean, you can ask this for lots of different classes of auctions. Let me tell you about one specific one. Single item auction, second price with bidder-specific reserves. Okay? One reserve price per bidder. This was the thing that had pseudo-dimension n log n we were talking about before. Okay? But now we're just thinking about an algorithm. So I give you T valuation profiles, each a vector of length n, and you choose n reserve prices, and you want to generate as much revenue as you can from your reserve prices for the valuation profiles I gave you. Let me make sure I'm clear on what I mean by a Vickrey auction with bidder-specific reserves, because there's actually a couple different versions. This is the version that's known as eager reserve prices. So how does it work? Okay, so suppose you set your reserve prices. What you do is you filter out everybody who didn't clear their reserve. Okay, so if someone goes below their reserve, they get deleted. It's as if they were never in the auction in the first place. Among those who clear their reserve, you just run a normal second price auction. Okay? So, right, so who's the winner? The winner is the highest bidder among the bidders that clear their reserve. Okay? Not necessarily the highest bidder overall, if the highest bidder did not clear its reserve. Right? The winner is the highest bidder who cleared their reserve. The price then is going to be the second highest bid by a bidder who cleared their reserve, or the winner's reserve price, whichever is higher. Okay? So that's what I mean by a Vickrey auction with bidder-specific reserves. Right? Filter out the bidders that don't clear it, run a Vickrey auction on top. Now notice, if you wanted to actually have an efficient algorithm for this, it's not immediately obvious whether or not one exists. Okay? Because there's n reserve prices, the number of things you might want to try is growing exponentially in n. So you certainly can't do exhaustive search. Can you do something clever? Well, one clever thing you could try to do is you could try to decouple the problem and reason about each bidder separately, okay, and just choose RI separately for each bidder. So to make sure that everyone's crystal clear on this problem, let me actually go through an example, which the point of this example is going to be to illustrate the tricky decoupling between the reserve prices of different bidders, okay? So what we have here, so we have n equals 2, so there's 2 bidders, and T, or S, equals 3. Okay, so there's 3 days or 3 samples. So this shows bidder 1's bids on the 3 days. This is bidder 2's bid on the 3 days. 4 and 2, this is going to be an initial set of reserve prices. We're going to look at how much revenue we get with these reserves. Then we're going to change the reserves and see how the revenue changes. Okay? All right, so suppose R1 is 4 and R2 is 2. How much money do we make on each day? Well, on day 1, both bidders clear their reserve. And the price is going to be set by bidder 1's reserve. So bidder 1 will pay 4, their reserve. So that's how much money we make day 1. Day 2 is similar. Right? Again, both clear their reserve, and this reserve is higher than this bid, so again, we'll make $4 from bidder number 1. Day 3, this is where bidder 2 wins. Okay? So bidder 2 wins. It doesn't pay its reserve, instead it pays a higher number, which is the bid of bidder 1, because bidder 1 cleared their reserve. Remember, the price is the higher of your reserve or the highest bid by someone else who cleared their reserve. Okay? So upshot, you make 4 every single day with these reserve prices. Suppose we jack up bidder 1's reserve to 6. Okay? What are the implications? Well, day 1, it's pretty clear. Day 1, it's a win, right? So bidder 1 still wins, but now it has to pay 6 rather than 4. Okay, so we gain 2. Second day, kind of we knew was going to be a loss, right? Because here it used to be that bidder 1 won. Now bidder 1 doesn't clear its reserve, so instead it defaults to bidder 2, who pays its reserve, which is 2. So you make 2 instead of 4, so that's the -2. The third day is the interesting one. The third day is where bidder 2 was the bidder winning. Okay, and we're only playing around with bidder 1's reserve price. So you should be thinking like, who cares, right? Bidder 1 didn't win on this day. However, by virtue of increasing bidder 1's reserve, now this bidder gets filtered out before the victory auction ever happens. So while it used to be the case that this bidder's bid set the price of the winner on the third day, now that the bidder's filtered out, we only get the reserve of the second bidder, 2, on the third day. So we actually lose 2 on the third day as well. All right? So overall, it's a loss. And again, the point here is to notice that when you play around with the reserve price of one bidder, there are implications for the revenue you make from the other bidders as well. Okay, and that's, once we saw these kinds of examples, we became convincingly convinced that this might be a formally hard problem. Okay. Any questions about the example?
This is because you're doing eager reserves.
Yes. Yeah. Right. So there's another version with lazy reserves, but there's various senses in which eager reserves are better. So.
Reserve is set by bidders.
Say it again.
So this reserve,
Yeah.
this is set by bidders.
No, it's set by the algorithm. So the green bars are what you get from the bidders.
This is the class of auction.
So the class of auctions we're talking about is personalized reserves. So single item auctions are personalized reserves. Yeah. Okay, so tricky coupling between the bidders, and indeed it is a hard problem. Okay, it's NP hard. It's even hard to approximate to within some constant factor. Okay, but there are efficient approximation algorithms, and so that's what I want to show you next. Okay, it's a very simple algorithm, very simple analysis. I'm going to show you this, if nothing else, so you get inspired to do something better. Okay, I hope you have a sense that something more sophisticated should be possible. I think that's true. So some nice open questions in this part. Okay, so the algorithm is just going to use the better of 2 possible sets of reserve prices. Okay? Now you always have the option of just not using any reserves at all. Right? Then you're going to collect the second highest bid on every single day. In some cases that's pretty good. Okay? But it's not good enough. Right? So maybe every day you have one high bid and everybody else is really small. Okay? Then you're going to need reserve prices. So the second option we come up with actually is computed by thinking about each bidder independently. Now we know from our example we're going to lose something when we do that, but fine, we can bound how much we lose. Okay? All right, so what's the optimization problem for bidder I? Well, when are reserve prices helpful? When do they make you more money than you would have otherwise? It's kind of in a limited case, right? It's kind of when you look at the bidder who's winning, their value is up here, the second highest bid by someone else is down here. It's reserves in between here that make you more money. Okay, as soon as you start beating out the second highest bid by somebody else, the revenue increases, and then once it goes to the valuation, it drops to 0. Okay? So that's the interesting region. For the winner, you choose a reserve between the second highest bid and their value. Okay? So QITZ, it's sort of a mouthful, but it's really what I just said. So for a given bidder I on a day T, Z is just the extra revenue you get from this region by setting a reserve price. Sorry, Q is the extra revenue you get from setting a reserve price of Z. Okay? So you only get a non-zero Q from a bidder on days where it's the high bidder, and then you only get it if Z is wedged in between these 2 quantities. All right? So that's the second option. Oh, and all right, so good. So what do? So for bidder I, you just choose the Z that maximizes the sum of these over all days T. Okay? In principle, there's an infinite number of Z's, but actually, without loss, you can set it equal to that bidder's value on one of the days. So there's actually only capital T choices of Z you need to try. Okay? So that can be done in polynomial time, and we just do it independently for each of the bidders. So it's certainly a polynomial time algorithm. Okay? All right, and you can prove a guarantee for it. You can prove that the better of these two options, or even a 50-50 mix of the two, is a 1/2 approximation, okay, of the most revenue you could get with any reserve prices. All right, so maybe I'll just state a key lemma real quick. So this is really just follows from some algebra and case analysis. I'll spare you the details. But the key lemma is to derive a particular upper bound on the maximum revenue that could be attained by any choice of reserves. Okay, so this is what we're comparing ourselves to. So let the optimal reserves be R star 1 up to R star n. By case analysis, you can prove that the revenue earned by this over all t days is at most the sum of the second highest bids plus the sum of the extra amount of revenue that you get from the reserves, where extra amount is defined exactly the same as the previous slide. It's the same Q values. All right? If you take this on faith, and you believe me that you can just prove this upper bound on the optimal revenue, then we're just totally done. Okay? It's clear that our algorithm is indeed a 1/2 approximation. Why? Well, this first term, right, this is exactly the revenue we would get if we took option 1, if we always used a reserve of 0. Okay? So that's one of our choices. This is, we choose, in option 2, we choose our reserves to maximize this quantity. Okay? So we would be even only higher than this second term. Okay? So our two options together cover all of this optimal revenue, so the better of the two, or even a random choice of the two, would give you a 1/2 approximation. Okay? So that's the whole analysis. Like I said, some really concrete, juicy, open questions for those of you that like approximation algorithms here. 1, do better than 1/2. 1/2 is tight for our algorithm, but I'm sure you're already getting ideas for what more sophisticated algorithms might look like. We can extend this result beyond single item auctions to matroid settings, but more generally, say for downward close settings, we don't know anything. We also don't know anything for more complicated families of auctions. So like one thing you could look at are what Jamie and I call T-level auctions, where you use T reserve prices for each of the bidders, not just one. Even for T equal 2, we have no non-trivial approximation results. Okay, so there's lots to do in this direction. All right, so that's what I want to say about the offline version of learning good auctions from bids. Let me say a little bit about an online version of the problem, okay? So here, you're not going to be giving all of the valuation profiles in a batch up front. Rather, an adversary will give them to you one by one, okay? So each day, there's going to be capital T days. On each day, you have to first come up with some set of reserve prices, okay, which you're going to use, or come up with an option. An adversary then provides you with a valuation profile. And you get whatever revenue you get, given the reserves that you chose and given this valuation profile. Okay? Now, this should strike you as pretty unfair. Right? Every day you have to go first, and then afterwards the adversary gets to try to screw you with a nasty valuation profile. So in these kinds of online learning problems, it's really important you choose the benchmark correctly. And the benchmark which works really well is something known as regret, which basically just says, well, let's compare how well we did over time to how well the best fixed action, i.e. fixed set of reserve prices, would have done in hindsight. Okay, that's known as the regret. Actually, we're going to need to have a weaker notion where we scale down the best revenue in hindsight by an alpha factor. So the standard regret would be when alpha equals 1, then this would just be the difference between how well you did and the best action in hindsight, but actually we're going to just compete with alpha times the best action in hindsight. Okay? Yep.
Isn't your data truncated because of the reserve prices?
Good question. Right. So another interesting question is where you have data that's censored in some way. So I'm approaching this problem from as if I'm Google, say, where I literally just have the bids. Right. So.
But your choice of reserve prices might.
Well, but people, you know, the advertisers still enter their bids. Right, so they may not meet the reserve, and they might really show up. But, yeah, so I mean, it sort of depends on how much information you have. But if you're a big data company, I don't think this is a real problem, actually. I think you have a sense of this, yeah.
Then how do we judge the efficient, this is whatever the mechanism that we are developing, and we are able to get solutions, right? And we are judging that this is efficient, something like that. So on what basis that this is the efficient one?
So by efficient, you mean economic efficiency or computational efficiency?
Like final, the option price, economical.
Yes. So in this setup, so we're looking at revenue for this entire talk. And in this context, we're looking at our average revenue. So how well we do. So here there's capital T days. So over here, this is just our average revenue over the T days. AT is the auction that we committed to. VT is the profile that the adversary gave us. Okay, so this is how well we did on average. And now there's this question of how do you know if that's a high number or a low number? So back when we were doing the statistical work, we could just use Meyerson's optimal auction as the benchmark. We could say, well, if our revenue was almost as high as the expected revenue of the optimal auction, then clearly we're doing well. In this online model, where there's no distribution, it's sort of prior-free and adversarial, you need a less obvious benchmark. But it is standard at this point, and that's this regret benchmark. So just the best that you could have done in hindsight. So you want to approach the best that you could have done in hindsight, at least up to an alpha factor. Yeah. Okay.
Non-trivial alpha is necessary.
It will be, yeah. I'll say a little bit more about that, yeah. For this problem, it is, yeah. Right, so again, if you've seen regret before, usually you see it with alpha equal to 1. Okay, but here we're interested in computationally efficient learning algorithms, and we will need to have alpha less than 1 for that to be possible. Okay. All right, so I don't have time for the details, but it turns out the same algorithm I showed you for the offline problem is easily extended to also give you an online algorithm which achieves this guarantee with alpha equal to 1/2, the same as our approximation factor for the offline problem. The key idea, the key difference is, our algorithm was deterministic, and in these regret settings, because you have an adversary, you need to be randomized. So there needs to be some way to inject randomization into our algorithm for there to be any hope. So we take inspiration from an algorithm known as Follow the Perturbed Leader by Kalai and Gompala, which basically says, inject some noise when you do optimization. So in our second option, where we choose a good reserve for each bidder, we actually solve a noisy version of the problem that they were solving in the offline case. Okay? So again, the main point to take away here is just it's a relatively simple variation on our offline algorithm that continues to work in the online case. And by work, I mean it has 1/2 regret going to 0 as t goes to infinity. Or put differently, the average revenue that you will get from using this online learning algorithm is approaching 1/2 times the best in hindsight as t grows large. Okay? Now, so when should I wrap up, Nikhil? Do I have 10 minutes, 15 minutes? Okay, good. So what did we just do? So we just took a 1/2 approximation algorithm for the offline version of computing good reserves, and we translated it into an online algorithm that was also efficient, which had no 1/2 regrets. But in doing this, we actually kind of really used specifics about what our algorithm is and how we analyze it. And in some sense, the moral reason why we were able to do this translation so easily is because our offline approximation algorithm has the special property of being, in some sense, maximal in range, meaning it exactly optimizes, up to a factor of 1/2, it exactly optimizes a certain upper bound on the revenue. Okay? So that's the key property it has that lets you do this. And so after we proved this result, Josh and I have gotten pretty obsessed with thinking more generally about offline to online reductions. So not just for an auction problem, but for any optimization problem. When is it the case that if there's a polynomial time alpha approximation for the offline problem, when is it true that there is also computationally efficient online algorithm with vanishing alpha regrets? Okay, so this is what we like. Black box fashion, you give me a good approximation algorithm, I'll apply some reduction, and I'll get a good online learning algorithm. So when is that possible? That's what we're interested in. It's probably intuitive, but it's not totally obvious that a reverse reduction holds. In other words, a necessary condition for having an efficient online algorithm with no alpha regrets, a necessary condition is that you have an efficient alpha approximation for the offline problem. In other words, the best case scenario would be a reduction of this type. The best case scenario is that in the online setting, you get an alpha which is just as close to 1 as what you could achieve in the offline setting. So that's the question. When can you do that, when can you not do that? So you might hope you could do it just always, okay, but that's in fact not true. There's an important result by Hazan and Koren, who exhibits an optimization problem where even if I give you an oracle for the exact problem that's efficient, you cannot in general get no regret in an efficient way. Okay. On the other hand, the answer is yes for a number of specific cases, right? So any linear problem, there's a very nice result by Kakadek, Klein, Leggett, which does this totally black box. So for any linear problem, you take any efficient approximation algorithm and turn it into a good learning algorithm. This maximal and range property that I mentioned in the last slide is another thing that allows you to do the translation. There's a Fox paper by Dudek et al. That made that sort of very general. And submodular optimization is sort of currently where the state of the art is. And again, a lot of algorithms can be translated. But we really do not understand fundamentally what it is that is allowing these approximation algorithms to be translated to online algorithms. So the big question here is, what properties of a problem, what properties of an algorithm allow you in a generic way to go from the offline case to the online case with no loss in the approximation factor? Okay, that's an open question, which I think is really not. It's purely algorithmic question. Okay. All right, so any questions about the second part, the computational stuff?
So regarding this black box thing, if you had a, so there's this thing for linear problems, if you had a convex objective, or I guess.
It is not known for convex, actually, surprisingly. As far as I know, it is not known for convex.
I guess since you're maximizing an concave objective.
Yeah, that's fine. As far as I know, there is not one known, which I find surprising. Yeah. For 8 years, we've had one for linear and not for concave. So that would be a very natural next step. I can double check that it's not out there, but I did search fairly hard for it 6 or 9 months ago and wasn't able to find anything, to my surprise. But you're absolutely right, that'd be a great next step. Yeah.
Alpha is alpha on the left and right can be off.
Say it again?
Alpha on the left box and alpha on the right box can be different, right?
Ideally not. So the alpha in the right box will only be worse. Okay, so that's what the reverse reduction says. So this alpha, if you have an alpha prime here, it can only go down. But it really seems like in an enormous number of cases, you can get alpha prime equal to alpha. And it's a little bit mysterious. So far, it's very algorithm dependent. Again, you use not just the algorithm, but you can use like the way that the algorithm is analyzed in sort of doing the translation. So it feels very ad hoc at the moment. There are subclasses where it's not ad hoc, we have something totally generic. But really, based on all of these great results in submodular optimization, I think something much broader should be true, but I don't know what it is. Yeah.
And so, like, are you looking at a specific kind of model, like the bandit model, or this is not even known if you know the full cost?
Yeah, so I'm even just talking about the full information model. Yeah, so like for example, so Josh and I have a recent result which is about a version of unconstrained submodular maximization, USM. So think like directly cut problems, that kind of thing. So basically, there's some ground set fixed up front, and then every day you get a submodular function, and you can pick a subset each day. Okay, so to be clear, it's not the ground set that's coming in online. Functions are coming in online, one by one. And again, you want to sort of have average value over time, competitive with the best fixed subset in hindsight, using a polynomial number of value queries.
And each day you get to know the entire system.
Exactly. I mean, there's work to be done extending it to bandit models. For some reason, my intuition is that's not where the separations are going to pop up. I'd be sort of surprised if you could do this in the full information model, but not in the bandit model. That feels sort of like not what the truth is. So at least personally, I feel like the most, where we're currently stuck is sort of fully present in the full information version. Yeah. Any other questions about the algorithmic part? Yeah.
I suppose that you are considering the valuation of the files fixed along this, for example, from day 1 to day 10. Is that right?
No. It's a new bidder every day, or a new valuation every day.
So the valuation the distribution of the value.
The distribution is staying the same. Yeah. Yeah, that's a good question. I mean, I would think you could extend this stuff. I mean, basically, it's going to sort of depend on sort of how rapidly they evolve compared to the sample complexity that's required. That's sort of what you'd expect. So you'd expect if they're evolving slowly enough, sort of on a slower time scale than what you need for convergence in the sample complexity world, you would expect to be able to track things. I don't think anyone's written out a proof of that form, but.
So you need a lot of further assumption to the evolved rate.
Yeah, I mean, Right, so I mean, it is interesting to think about, in machine learning parlance when your test distribution is different than your training distribution. But I mean, the basic issue, I mean, there's sort of so many challenges already in the standard PAC model where you have the same distribution for training and test data. That seems like, in 2017 kind of the natural thing to focus on. That said, I would welcome work that extends this to where you have, evolving distributions and so on. Yeah, but that hasn't been my focus so far. All right, so let me just say a little bit about strategic aspects of the problem. There's been a couple of questions addressing this already. And so here, the work I'll talk about on my own is joint with Oka Scrivers, who just graduated from Stanford. He's now at Facebook. This paper appeared in NIPS a week or two ago. So as several of you have pointed out, what we've been assuming so far is that the bidding data is truthful, or at least that we can figure out bidders' valuations from the bids that we saw. And in some cases, this is going to be a reasonable assumption. Okay, so for example, if first of all you're running a truthful auction, and second of all, a bidder only participates in one auction, then it's reasonable to expect they would bid truthfully. Okay, so in this interpretation of the learning model, you're not seeing literally the same bidder number one every day. You're seeing new representatives from some population of possible bidder number ones every day. Or even if bidders are persistent and they stick around, you might say, well, maybe they reason myopic, or maybe they just try to maximize their utility independently in each of the auctions they participate in. Then again, this would be a good assumption. But you still got to be worried about the case where bidders are both persistent, participate in a bunch of auctions, and also strategic. They sort of think long-term about what to do. And the particular sort of, failure mode you might be worried about is that, suppose you're trying to use someone's bids to set reserve prices in the future, you might be worried about the bidder sort of artificially bidding really low for a while so that they get a low reserve price in the future, okay? So that's a really interesting issue. There's been a lot of work on that in the last few years in the AGT community, which I don't have time to tell you about in detail, but I encourage you to check it out. The one probably closest to the stuff I've been talking about is this paper of Kanoria and Nazarzadeh. They basically show that, even if bidders are strategic and persistent, at least if they're IID or close to IID, then you can actually get all of the results I've been talking about today with no assumptions of myopia at all. Okay, so you get exactly the same kind of convergence results. The intuition for that result is that in a close to IID case, you can set reserve prices using only the bids of other bidders. Okay, and that's enough to get all the results I'm talking about to go through. And then a lot of these other results work on different models with some quite interesting game theory. But yeah, so that's sort of that's another direction which we're seeing a lot of cool work in. I'm actually not going to talk specifically about that problem, so I'm going to talk about this paper with Oka, which it's not about auctions, it's about learning to make good predictions from expert advice, but it still is sort of addressing the same issue, where you have people you interact with many times over time, and you're worried about sort of the incentive compatibility of the auction that you run. All right, so before I tell you about our model, let me just say what the classical model of online prediction is. So again, there's going to be capital T time steps. And imagine that at each day t, you want to predict some outcome, let's say a binary outcome. Like you want to know, is it going to rain tomorrow or is it going to be sunny? Okay. You have some clues about the answer in the form of expert advice. Okay, so any different people give you their opinions. Like you look at a bunch of different weather forecasters, see what their probability of rain is. Given all that expert advice, you have to then make a prediction. You have to either bring an umbrella or not. Okay? Then the event is realized. You find out if it rained or if it didn't rain, and everybody incurs some loss. So the loss function here is a parameter of the model. It could be squared loss, it could be absolute loss. There's lots of sort of standard natural loss functions. So for example, if it rained and you didn't bring an umbrella, you will have some loss. And similarly, you can think of each expert as incurring a loss, which would be, basically if you took their advice at face value, what would your loss have been? Okay? So that's classical online prediction. So the question is, you keep getting advice from experts. You'd like to make increasingly good predictions over time about what's going to happen. Okay? So there's a famous algorithm, has many names, but let's call it the multiplicative weights algorithm, with a classical guarantee. And so the algorithm is very natural. Right? So it maintains a weight for each of the experts. This weight is sort of a proxy for the expert's credibility, how much you believe it, and that's based on past performance. Okay, so experts who have been accurate in the past will have high weights, those who have been inaccurate will have low weights. And then the algorithm is very simple. Basically, you make your prediction just by taking a weighted average of the expert predictions, okay, with these weights that you're maintaining. And the classical result here is a no regret kind of guarantee. Okay, so if you evolve the weights in the right way, then in fact the average loss of your prediction algorithm will be competitive with that of the best expert in hindsight. Okay? So this is the old model. So it's known how to compete with the best expert. So the twist in our model is we allow these experts to be strategic. Okay, so what's different now, everything's the same. Each expert still has some true belief about whether it will rain or not, but now they're allowed to report whatever they want. Okay? And they can lie if it's in their interest. Okay, so why would it be in their interest? Okay, well, what do experts want? So the utility model is going to be a very simple one. We're going to be assuming that you're using some weight update-based algorithm, like multiplicative weights. We're going to assume that each expert wants to maximize their own weight. Right? That's sort of like their public reputation. That's like the number of stars that they have on Yelp, in effect. Okay? So we assume that agents report in order to maximize their expected weight in the future. Okay? So that's the question. So what happens? How do things change when experts are strategic? All right, so let me just sort of briefly highlight some of our results, and then I'll wrap up. So the answer depends on the choice of the loss function. And actually, what's cool is there's one standard loss function, squared loss, where actually the standard multiplicative weights algorithm is just out of the box incentive compatible. By incentive compatible, I mean that every agent is incentivized to report their true belief. And that's true even if they're reasoning over the entire time horizon. Their best strategy is to just report their true belief every single time step. And the reason this is true is because when you have this squared loss function, it turns out the standard multiplicative weight update is closely related, basically an affine transformation of what's called the quadratic scoring rule, which is a strictly proper scoring rule incentivizing people to report their true beliefs. So sort of inadvertently, if you happen to have this loss function, multiplicative weights is using a strictly proper scoring rule, it turns out. Now, if you change the loss function, that's no longer true, like for absolute loss. So here, instead of squaring the difference between your prediction and what happened, we just take the absolute value. So here, actually, the standard algorithm is not incentive compatible. And it's very easy to explain, actually, what goes wrong. What goes wrong is experts are incentivized to report extreme opinions. So if you believe the chance of rain is 51%, actually it's in your interest to report a probability of 100%. If it's 49%, it's in your interest to report 0%. Those are the incentives faced by the experts in the standard algorithm with the absolute loss function. So could you do anything different? Can you recover incentive compatibility and recover the guarantees of the classical algorithm? Well, not completely, but to some extent, yes. So we can show that actually there is no online prediction algorithm, incentive compatible or not, which enjoys the same no regret guarantee as the multiplicative weights algorithm in the case of honest experts. So there really is a cost in terms of regrets when agents are strategic rather than honest. You cannot get the same guarantees. On the other hand, you can get pretty close. Okay? You can get within a small constant factor. So we propose a weight update rule which is based on a strictly proper scoring rule known as the spherical rule, and then you do get competitive with the best expert in hindsight, at least up to a small constant factor. Let me take it at the end. Yeah. Okay, so let me just kind of wrap up and remind you what we talked about through a few open questions. So in the first part of the talk, we were just looking at purely statistical questions. What's the sample complexity of learning good auctions? How much data is necessary and sufficient? There's been a ton of progress in the last couple of years. So the state of the art has actually gotten pretty impressive recently. But still, there's an opportunity to have better results for multi-parameter problems. So there, the state of the art is a very nice Fox paper by Kai and Daskalakis, but I fully expect there to be further extensions and generalizations in the next year or two. We mentioned about how for the computational problem of computing a good auction, computing good reserves, tons of very concrete open questions for those of you that like approximation algorithms. Like I said, I'm pretty obsessed with this idea of why are all these offline to online reductions possible? I would like a general theory of when those exist. And then our last topic was this strategic issue of when you have bidders that are both persistent and strategic, what implications does that have for trying to maximize your revenue by learning from bidding data? As I mentioned, there's been a lot of exciting work in that direction, but it's still pretty wide open. I think there's lots of opportunities for further work. So let me stop there. Thanks.
Next on the agenda is business meeting.
HTML.
HTML.